Okay, and you had her last year. Okay. These are not in the Math 3 curriculum, so Ms. Martin was just doing a little extra. Coach Wood has not let you down necessarily here.
We definitely didn't even finish the Math 3 curriculum.
Yeah, he was.
Billy, he told us he just told us not to do anything like that.
Yeah, he.
Coach Wood said, do your IXL and use Desmos.
Yeah.
We never did a lesson. We never did an actual lesson in there, ever. One problem maybe, if you asked for help, he gave you the answer. It was lovely.
Yeah. So,
The test was
so secant, cosecant, and cotangent, unless you happen to get a little extra in Math 3, should be new functions for you. So secant is 1 over cosine, cosecant is 1 over sine, and cotangent is 1 over tangent. Okay, these are known as the reciprocal functions because when you do 1 divided by something, it just flips whatever you have down here. So I typically, when I teach these, I tell students to remember that they have to have a co with every pair because you'll have to have these memorized. None of this will be given to you. So it's pretty obvious that tangent and cotangent seem like they should go together, although sine and cosine seem like they should go together and they don't. So that may not be the most help, but cotangent and tangent do go together. Sine has to go with cosecant because there has to be a co there. It can't go with secant because when you have sine secant, you wouldn't have a co at all. Secant has to go with cosine, right? Because you can't have cosecant and cosine together. You'd have 2 cos. That would not work. So that helps me remember which one is which here as far as secant and cosecant. Cotangent, just remember those go together like they seem like they should, right? So secant is 1 divided by cosine, and cosecant is 1 divided by sine. Because cotangent is 1 over tangent, and tangent is sine over cosine, right? So if I'm doing 1 over sine x over cosine x, right? Dividing fractions is easy as pie. I flip the second and multiply. Cotangent can also be given as cosine x over sine x. So this is another way that you could write cotangent. It's the reciprocal of tangent, right? Tangent is sine over cosine. We flip it and we get cosine over sine. So when we're asked to do anything with secant, cosecant, or cotangent, we're really going to base it off of what we already know about the sine, cosine, and tangent functions that go with them for that. And so there are going to be a couple things that we have to do with this. We're going to have to think about their graphs, and we're going to have to think about their solving equations with these. So secant is going to look like this. Now the dotted line right here in the middle is not part of the graph for secant. The dotted line here in the middle, this dotted line right here in the middle is cosine of x, right? It's not part of the graph. But secant is 1 over cosine. So I want you to notice something here. Every time cosine equals 0, what do you see happening on your graph? Every time cosine has an x-intercept there, you have a vertical asymptote, right? Think about that because every time cosine equals 0, 1 over cosine is undefined, right? So every time cosine equals 0, you've got a vertical asymptote. And then basically like where you would have a maximum, it is a minimum on the, a maximum on cosine would be a minimum on your secant. It's just sort of inverted there. So you get this kind of weird graph here. As this sort of makes sense there. So your asymptotes are like pi over 2, and the next one's 3 pi over 2, and 5 pi over 2, and 7 pi over 2. They are separated out by pi, right? Those are where your asymptotes are going to be. This is for secant. Okay. Right. Yeah. That was smart to not let him take it with him.
All I know is I see you going around doing this all day.
Oh yeah, that's exactly what he would have done. Yes. Yeah, there's some similarities I see between you and my son.
You can prepare yourself for whenever you're
I know. Sometimes I look around at Hunter and then at other people and be like, "Oh, is this what Lucas Hampton was like in middle school?" Maybe. Not really.
I'm mature since
So,
are you pushing?
my license now.
How do you know that's age?
I'm just saying, just make your body.
and a driver's license. That's scary. That's scary. Just thinking that he's
How
gonna
old
be.
is he?
He's
Is this the little
13.
bitty one that was in here that day that I was in here late?
That was probably Henry. I mean, Hunter's not big for his age, but Henry's only 7.
No, this one was he was with redhead. It was a redhead kid with him.
That
Tall one maybe or something.
yeah. Oh, that was Hunter. Yeah,
That was
yeah. He's small for his age. Although we did go to Dr. Chu's yesterday, and Dr. Chu every time we go talks about how tall Hunter is. Which, to be fair, he is almost as tall as Dr. Chu right now. So yeah.
He'll grow.
Yeah. All right. So this is secant. Secant is based off of cosine. Cosecant is based off of sine. So the only thing that happens with sine and cosine is that they're just shifted over a little bit, right? So cosecant is just going to be the same graph as secant, except for it's shifted over a little bit. Notice right here, this is the graph here of sine of x. And every time sine of x equals 0, what do we see on our graph of cosecant? Vertical asymptotes, right? So whenever you have sine equal to 0, that's where you're going to see vertical asymptotes. Those vertical asymptotes are going to be at pi times an integer, so like 1 pi, 2 pi, 3 pi, 4 pi, and so on for that. Did he ask this? Yeah, he did. Okay. Actually, did he? What is the period of these graphs? It is still 2 pi. Because although your vertical asymptotes are only separated by pi, if you kind of think about tracing the graph, I'm going to use cosecant because it's a little easier to see. Here you go 0 to pi, and you have vertical asymptote, but it's not repeated yet because you still got this negative part right here, right? You got to have both sections before it starts to repeat. So unless I'm missing it, he didn't put the period anywhere here. I don't think, unless it was up earlier. Yeah, he didn't put the period there. So let's add that period of secant x and tangent x is 2 pi. Right, so same as sine and cosine, which should make sense because they're based off of sine and cosine. So they should have the same period as sine and see, cosecant, not tangent. I don't know what I'm thinking. Cosecant there. The ranges on these, where sine and cosine can only be between -1 and +1, you'll notice that secant and cosecant are everywhere except for that, right? all of these values are below -1, and all of the values up here are above +1. So your ranges for secant and cosecant are from -infinity to -1 and 1 to infinity. You will not have any of the values between -1 and 1 for these functions. For that. Okay, so that's what these look like. Cotangent. Cotangent is going to look a lot like tangent, but there are some differences. Tangent has vertical asymptotes at -π/2 and +π/2. Cotangent is going to have vertical asymptotes at increments of pi, so 0, pi, 2 pi, 3 pi. So it's sort of slid over. And tangent, the tangent graph has sections that look like this, right? Your sections are increasing the whole time. Cotangent, you should see a decreasing pattern there. So it's really just like a reflection of tangent, and it slid over for that. The period for cotangent is just pi. Period for tangent is pi. Period for cotangent is just pi. Now, notice here, cotangent of x is 1 over tangent, but it's also cosine x over sine x. So, if sine x equals 0, cotangent x has a vertical asymptote. So if you think about that unit circle, right here is 1, 0, cosine is 0 at 0. So right here at 0, it's not really drawn in because the axis is there, but you got a vertical asymptote. And then that happens again over here at pi. That is -1, 0. And so at pi, sine is 0, you have a vertical asymptote. And that's just going to happen every increment of pi. So thinking about it as whatever the bottom of the function equals 0 helps me remember where the asymptotes are at, because otherwise I think it's hard to remember those here. For that, your range, he didn't put this here, but or maybe he didn't know. Range is just -infinity to +infinity for that. Okay, questions so far? All right, so usually I think the types of questions you're going to see for these are going to ask about your vertical asymptotes. So if we look at example 1, it says let f of x equal 3 secant of 2x. The only thing that is going to affect where your vertical asymptotes are is if you shift left or right. Does this have a, well, actually, no, that's not true. If you shift left or right, or you have an expansion or compression. We don't have a shift left or right, but we do have a compression on this one. What we want to think about for this is really about this graph, f of x, is really, we can kind of keep the 3 out here. Secant is 1 over cosine of 2x, right? Or secant of 2x would be 1 over cosine of 2x. The 3 is just a vertical stretch. It is not going to change anything about where our asymptotes are in the graph. So we don't have to really think about that very much. But I know that if the denominator of this function right here, if that equals 0, then I'm going to have a vertical asymptote at that point. So the way I like to think about this is I think about where cosine of 2x equals 0. And it's kind of weird that you got that 2x in there. You may want to like divide it off or something, but you can't do that when it's on the inside of the function. So what we're going to do is sort of think about doing this. To get rid of cosine, we do cosine inverse. And remember that cosine inverse means where does cosine equal 0? Where does cosine equal 0? right here at pi over 2. Now, we might end up having to use like a different spot. It also equals 0 down here at -1. If pi over 2 doesn't work, maybe we need to use 3 pi over 2. We're going to hold off on that because it's not our principal values. But maybe. If this one doesn't work, maybe we will need to do that. So that means instead of having x equals pi over 2, we're going to have 2x equals pi over 2. Because we had that 2x on the inside. That 2 is still there, right? And so if I want to figure out this, I just need to divide by 2. Or in this case, since I got a fraction over here, is it all right with you guys if I multiply by 1/2? That'd be the same as dividing by 2, and it makes it a lot easier to do over here on this side. So 1/2 times 2 is just 1, that goes away. And then I'll get pi over 4 here. And that is an answer choice, so I don't have to worry about trying to do that 3 pi over 2 for that. We would also have a vertical asymptote at 3 pi over 4. If I did the same thing with 3 pi over 2, I'd get 3 pi over 4. But it's only asking me for one of those, and we have an answer choice that is correct here.
Wait, why did we put the 1 on top of the cosine again? Because we had a compression?
Secant, not because of the compression, but because secant equals 1 over cosine.
Oh.
And since secant is not on the unit circle, like you could do this by thinking about what secant looks like, but since secant is not on the unit circle, it's a little hard to think about, but cosine is a little easier to think about. Questions there? All right, 2's asking us about vertical asymptotes of g of x. This time it's a cosecant function. What does this 4 right here do to the graph?
It would be like adding 4 on the end.
It's the same as like adding 4 over here on the end, which would up 4. Is that going to change where your vertical asymptotes are at? It will not. The negative flips it. If you flip it, does it change your vertical asymptotes? It will not. The 2 is a vertical expansion. Again, doesn't really matter for your, anything vertical does not change your vertical asymptotes. It's only the stuff on the inside, right? So it's really, we don't even really have to consider that. We just need to think about this part, right? Cosecant is 1 over sine. So this is going to be 1 over sine of pi x. And what we're looking at is we're going to have vertical asymptotes anytime that denominator equals 0. Right? So much like we did on the last problem, we want to set that equal to 0. So sine of pi x will equal 0. And we're trying to solve for that x right there.
You have to do the inverse of sine.
Yes. I'll do inverse sine here and inverse sine here.
Does it do anything to the 0? Or just do cancel?
When we do sine inverse of
Oh, it's
0,
where does it
it means
equal 0?
where does sine equal 0? So if I think about the unit circle, sine is my y coordinate. It's going to equal 0 at 0 right here. Now, if it's 0, my answer is going to end up being 0, right? Is that any of our answers?
No.
So I don't think 0 is the one that they used. So where else does it equal 0?
Pi.
Pi over here. I bet that this is the one that they use. So let's try that. We got pi times x will equal pi. What do I need to do to solve that for x? Divide by pi. And so x would equal 1. So x equals 1 would be the answer. If x equals 0 was there, it would also be an answer. But they didn't use that one. They used this one. And really, like 1, 2, 3, 4, 5, all your integers are going to be answers for this, but they won't give you more than 1 for that. Okay. Questions so far? All right. For 3, it gives us 3 cosecant of theta over 2. Which of the following gives the range of h? Range is our y values, right? So, will it affect y values at all that we got this over 2 on the inside?
No.
That is horizontal, right? And so that affects your x values. That squishes it in or stretches it out. So that's not going to affect the range. It's the 3 out here that's going to affect the range right there. It's going to make everything triple on the y-axis. Now, normally, if we think about like cosecant is 1 over sine, right? Sine, if we had a sine instead of a cosecant, we'd have an amplitude of 3. So what's going to happen, if we think back over here on this graph, like here, this was the graph of sine, right? And it fit perfectly in here. So if I've got 3 cosecant, it's like the sine graph was multiplied by 3, and it's going to make it 3 times taller, right? Which means where our range right here just goes from negative infinity to negative 1 and 1 to infinity, our range here will go from negative infinity to negative 3 and 3 to infinity right here. So your sine values would be from negative 3 to 3. The cosecant values are like the other stuff of that, like negative infinity to negative 3, 3 to infinity. Does that make sense?
Yeah.
Yeah. All right, questions so far? All right, 4 might be the trickiest that we've had yet. It says that we've got negative 5 cotangent 2 pi x. Which of the following is the vertical asymptote of k? So, is the negative 5 going to affect vertical asymptotes of this graph at all? It will not. It's only the stuff on the inside, right? And when I'm thinking about vertical asymptotes, I'm thinking about the denominator equals 0. Right? So cotangent, I could think 1 over tangent, but I don't know tangent values very well either. It's going to be easier to think of this as your k of x equals the negative 5. That negative 5 doesn't do anything. Cosine of 2 pi x divided by sine of 2 pi x, right? And the denominator cannot equal 0. If my denominator equals 0, I'm going to have a vertical asymptote. So, much like we did on the other problems, we're thinking about where sine of 2 pi x equals 0. Okay, so we get that sine out of there. And so when we do sine inverse, we're asking ourselves, where does sine equal 0? And we just did that, right? Unit circle. Sine equals 0 at 0, but does it look like that's going to be an answer? Because I don't have x equals 0. It's probably going to be the pi over here. So let's use pi right there. And then I need to divide by 2 pi. Remember that pi on top has a 1 with it, so the pi's will cancel, and we will get x equals 1/2. And so that would be a vertical asymptote. I put my jacket on a minute ago, but I don't think it immediately got cold. Okay. Now, the other thing, so one thing we might be asked to do is be asked to talk about the graphs, particularly the vertical asymptotes, or possibly the range for those secant and cosecant. They're probably not going to ask you about range of tangent or cotangent because it's just always negative infinity to infinity. But the secant and cosecant they may ask you about. The other thing we need to be able to do is we need to be able to solve some equations dealing with secant and cosecant and cotangent, which we're going to see is pretty similar to what we were doing yesterday. There's just going to be like one twist for that. So here it asks us, it tells us f of x equals 4 cosecant x plus 3, g of x equals 11, in the xy plane, what are the x coordinates of the points of intersection of the graphs of f and g? So if we want to see where two graphs intersect, algebraically, we just set them equal to each other, right? So they could have just asked us to solve this equation for cosecant of x plus 3 equals 11. All right, so first steps are like they always are in solving equations. We just need to subtract that 3 for cosecant of x will equal 8, and then we'll divide the 4, and so we're getting cosecant of x equals 2. Now, I don't know cosecant values on my unit circle, right? I could find them out, but they're not. You have to do 1 over whatever your sign is, and you have to test all these points. So it'd just be a lot easier if I just change this equation to signs, right? So cosecant is 1 over sine of x would equal 2. Now, you got some options here. You could cross multiply if you want. You get 2 sine x equals 1, and then you can divide off that 2. So sine x will equal 1/2. Another option here is cosecant and sine are reciprocal functions. So if cosecant of x equals 2, which is like 2 over 1, then sine of x is just going to equal 1/2. The fraction flips. So you don't necessarily have to do all that work. You can just flip it, and that is going to give you the reciprocal function for that. Now, sine of x equaling 1/2, that is just what we were doing before, right? So what you want to do is you want to solve it down till you get your secant or your cosecant like it was, then change it to sine or cosine, and you'll be able to answer that from the unit circle. So on the unit circle, we're looking for where sine, which is my y coordinate, equals 1/2. That's going to happen right here at pi over 6, and over here at 5 pi over 6. So x would equal pi over 6, and x would equal 5 pi over 6. And this restricts me to the unit circle, so those would be my answers. Okay, questions? All right. 6 is a secant problem, very similar to what we just did. Let's do this one. You're looking for intersections. You're just going to set your two equations equal. So we're going to have 3 minus 1/2 secant x equals 4. We will need to subtract that 3, negative 1/2 secant x will equal 1. And then I need to divide by negative 1/2. Or I probably, if I was not doing this for your benefit, I would have just multiplied by a negative 2. Because if I multiply by the reciprocal, that's the same as dividing by that fraction. So secant of x here, dividing fractions, is easy as pi 1 times negative 2 over 1. You're going to get secant of x equals negative 2. Now, the easiest way to do this is just think about the reciprocal functions, right? Secant is 1 over cosine. So right now, this is negative 2. That means cosine of x would be negative 1 over 2, right? We just flip the fraction. Secant and cosine are reciprocal functions of each other. Does that make sense? You could also do like the equation like I did earlier, but this is really the fastest way to do it. And then now we're just thinking unit circle. Cosine is my x coordinate. My x coordinate is going to equal, well, it'll be positive 1/2 right there. It'll be negative 1/2 right here at 2 pi over 3. And then also down here at 4 pi over 3. Questions? All right, so example 7 is a calculator active problem. We really have not used our calculator much in this unit at all, and we won't much, but here's an example of somewhere you might would. This is asking us for where, it gives us p of x, and it's asking us where p of x equals 2. So we would take our equation for p of x, 3 minus 1.7 cotangent of 0.5 x minus 1, and set that equal to 2. And so we would start by just subtracting that 3. And so we'll get negative 1.7 cotangent of 0.5 x minus 1 equals negative 1. And then we would need to divide by that negative 1.7. And let me grab my calculator here. So we're getting negative 1 divided by negative 1.7. We'll get 0.588. Keep that number in your calculator. We got cotangent of 0.5 x minus 1 equals 0.58823, and so on. Keep that number in your calculator. You don't want to round till the very end of this. Now, does your calculator have an inverse cotangent? Because we got to get rid of cotangent, and these are definitely not unit circle values, so we're not going to be able to use the unit circle on this. That's why they're giving us the calculator. Your calculator does not have inverse cotangent values on it. All right, you have an inverse tangent right here. If you hit the blue button, and tangent, but you don't have inverse cotangent. But tangent and cotangent are reciprocals, right? Right now, this is 0.58823 and so on over 1, right? So if I switch this to tangent of 0.5x minus 1, what will I get over here? 1 over that big decimal, 0.58823, and so on. So tangent of 0.5x minus 1 is going to equal 1 divided by that number up here, and that gives us 1.7. I could have made my life easier here, couldn't I? Because this fraction was 1 over 1.7. If I had just went ahead, if I didn't do the decimal, I would have had cotangent equals 1 over 1.7, and then I could have switched it, and I would have just got the 1.7 there. So the decimals were kind of unnecessary, but either way, it works out. To get rid of tangent, what have you got to do? Inverse tangent. So inverse tangent over here will cancel. Inverse tangent over here, we're going to have to use our calculator for it because these are not unit circle values. So we'll do inverse tangent. To get to that, you're going to hit the blue button and your tangent button, and then 1.7, and you should get 1.03907. And now we're just down to a simple two-step equation to solve. So you would add the 1. So 0.5x would equal 2.03907. And we'll divide by 0.5. And x will equal, that's going to be 4 something. 4.078. I'm going to go ahead and round it off at this point, 0.078, because this is our final answer, and we don't need to keep any more decimal places now. So if you have secant, cosecant, or cotangent in an equation that you have to solve, you just want to flip it so that it's not secant, cosecant, or cotangent, because you won't know how to do it using those values. Okay. Any questions there? All right.